Okay, let's dive into this. Welcome to The Explainer. Today, we're looking at something we literally experience every single second of our lives. Yet, let's be honest, we rarely pause to truly dissect it. We're talking about gravity. But don't worry, we aren't going to get bogged down in dense theoretical physics or high-level cosmic debates today. Instead, we're demystifying gravity by framing it strictly as an operational concept. We're going to look at why the underlying mechanism, the ultimate why behind it all, actually doesn't matter one bit for everyday practical physics.
To get started, I want you to just picture something super simple. Imagine a heavy, hardcover book slipping from the edge of your table. It drops straight to the floor, right? Or think about that distinct resistance you feel in your muscles when you try to lift a heavy stone off the ground. It fights you. It clearly wants to stay low. In everyday life, we just slap a convenient label on this whole experience and call it gravity. But we have to address the mystery that has plagued scientists, philosophers, and basically anyone who's ever dropped anything for centuries. Why do heavy things actually fall? What is literally happening here?
Think about it. When you drop that book, is there some invisible magnetic-like force reaching out from the center of the earth, grabbing the book and actively pulling it down? I mean, we've been taught since childhood to visualize gravity as this grand, invisible tether. But how do we know for absolute sure that the ground below us is the thing doing the pulling? What if we're looking at it completely backwards?
Let's just entertain some alternative ideas that have actually popped up throughout history. Is atmospheric pressure actually pushing down on the object from above? Or, perhaps, is it just an intrinsic property of matter to naturally seek out the lowest possible resting point? These questions about the origin of gravity are, without a doubt, incredibly fascinating. People have passionately debated them for hundreds of years. But here is where we make a sharp pivot in our explainer. Because while origin stories are really fun to ponder, for practical, everyday physics, they are completely unnecessary. We're going to treat gravity as an operational concept. So what does that mean? An operational concept is simply a measurable, predictable rule of thumb that describes how things move, completely regardless of why they do so. And honestly, that is the ultimate narrative bait and switch. I'm relieving the tension for you right now. You absolutely do not need to know the origin of the universe to understand how a falling rock behaves. In the practical study of forces, motion, and stability, gravity just isn't treated as a rigid metaphysical truth. It's simply a highly reliable tool. The ultimate origin or cause of gravity is totally irrelevant when you're just trying to study its behavior in daily life. Now, to really master this operational approach, we first need to define what a force actually is. A force is literally just a push or a pull acting upon an object that results from its interaction with its environment, and we use it to quantify change. That's it. It's just a relationship, a practical mathematical tool. So when we analyze an everyday system, whether we're calculating the stopping distance of a car slamming on its brakes, predicting the swing of a grandfather clock's pendulum, or just a person standing on a bathroom scale in the morning, we're looking purely at the effects of these forces. We aren't analyzing their deep philosophical beginnings. We are just measuring the push or the pull.
And this brilliantly illustrates the point. Think of a mechanical wind-up clock. If you want to use that clock to tell time, or if you need to calculate the speed of its gears, or fix a stuck second hand, what do you really need to know? You only need to understand the mechanical relationship between the springs and the cogs. Asking who wound the clock is totally irrelevant to your math. It really doesn't matter if it was wound by a human hand, a machine, or a falling weight. The input energy manifests as a predictable turn of the gear. Well, gravity in everyday physics is exactly like that turning gear. We don't need to accept on faith that the Earth's core possesses magical pulling powers just to calculate how fast an object will hit the ground. We just need to observe that a consistent downward push or pull exists.
Moving on to Section 2, Gravity in Static Systems, the constant counterweight. Let's look at stationary objects for a second. Imagine a heavy laptop sitting quietly on top of a sturdy wooden desk. It isn't moving, obviously, but forces are absolutely at play. Even if you totally reject the idea that the Earth is actively pulling that laptop, the physical reality right in front of you doesn't change one bit. It is undeniably pressing down. In physics, we label this downward pressure as F subscript g, which stands for the force of gravity, or simply weight. What's really interesting here is how an engineer views this. If you were tasked with building that desk, your sole concern is the magnitude of this downward force. You just need to make absolutely sure the desk exerts an equal and opposite upward force so the legs don't snap under the pressure. You measure the downward force directly with a spring scale, and you design accordingly to keep the whole system static.
Let's look at 3 totally irrelevant causes of that downward pressure. 1, the Earth is pulling it. 2, the air above is pressing it down. Or 3, a natural preference for the object to rest as low as possible. Notice how the cause didn't change the math at all?
Because this downward force is constant and measurable, we treat it purely as a concept of force to ensure our structures don't collapse. Whether the push comes from above or the pull comes from below, the origin story of the force changes absolutely zero calculations. The desk still has to hold up the exact same amount of weight.
Let's move to and see how this builds when things are in motion. Section 3, Gravity and Dynamic Systems, Predictable Acceleration.
So if you hold a set of keys in your hand and let them drop, they start at a speed of exactly 0, but instantly accelerate toward the floor. Every single object accelerates at the exact same localized constant rate. When analyzing this motion, physicists use a brilliantly simple mathematical framework: force equals mass times acceleration. We observe the mass of the dropping keys and we observe their acceleration. By multiplying those two observable facts together, we calculate a force. This force isn't some mystical energy beam. It's just a clear mathematical description of the physical hustle that the object exhibits while falling toward the floor. It's an equation that reliably describes a predictable reality.
Now, consider a hypothetical skeptic who says something like, the Earth isn't pulling that object. Rather, the object is just seeking its natural density layer. Honestly, this is a perfect example to prove our point, because even if someone fully rejects the mainstream theory of gravity and believes this quote instead, guess what? The math remains completely identical. The object still hits the ground at the exact same millisecond with the exact same amount of impact. The operational concept of gravity allows us to perfectly predict exactly when a dropped glass will hit the kitchen tiles and shatter. The concept works flawlessly, completely independent of whatever underlying mechanism you believe is responsible for the drop.
Which brings us to Section 4, the practical utility of concept over cause. Studying gravity as an operational concept is honestly incredibly liberating. It frees us from needing to blindly accept invisible mechanisms on faith. You don't need a deep belief in the curvature of spacetime to know how to build a safe ladder. Everyday human reliance on gravity is literally everywhere once you start looking for it. First, we have plumbers. Plumbers design drainage pipes with a specific downward slope, relying entirely on the fact that liquids will always consistently move toward the floor. Next, we have construction workers. They use plumb bobs, which, are basically just weights on a string, to ensure walls are built perfectly vertical. That string pulls taut in a straight line toward the ground every single time, without fail. And finally, weightlifters. They know for a fact that adding more iron plates to a barbell increases the downward force they must physically overcome. The plumber, the builder, the athlete, they don't care about theoretical origins or the magnetic core of the Earth. They all successfully rely on gravity simply as a conceptual, highly predictable downward push. Which brings us to our final takeaway for today. The cause can absolutely remain a mystery, but the force is a functional reality. Gravity, at its core, is just a description of behavior, not an explanation of intent. It's just a label we give to the undeniable, measurable, daily experience of weight and downward acceleration. You don't need to believe in a magnetic core or spacetime or any complex third-party scientific theory to utilize the physics of gravity. By treating it strictly as a reliable downward push, anyone can accurately calculate and master their environment. So the next time you drop something, I want you to ask yourself a question. Does it really matter why it fell? Or is it enough to know exactly how it falls so you can master your world?